Hello, good morning. Welcome to Advent of Code 2022. Done in Kotlin, day 10. Cathode-Ray tube. You avoid the ropes, plunge into the river and swim to shore. The elves yell something about meeting back up with them upriver, but the river is too loud to tell exactly what they are saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritized getting the communication system on your handheld device working. You pull it out of your pack, but the amount of water slowly draining from a big crack in its screen tells you it probably won't be of much immediate use. Unless, that is, you can design a replacement for the device's video system. It seems to be some kind of cathode-ray tube screen and simple CPU that are both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. Start by figuring out the signal being sent by the CPU. The CPU has a single register X which starts with the value 1. It supports only two instructions, add X, Y. Takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. No op takes 1 cycle to complete. It has no other effect. The CPU uses these instructions in a program, your puzzle input, to somehow tell the screen what to draw. Consider the following small program: no op at x3 at x minus 5. Execution of this program code program proceeds as follows. At the start of the first cycle, the no op instruction begins. Execution. During the first cycle, x is 1. After the first cycle, the no op instruction finishes, executing, doing nothing. At the start of the second cycle, at x3 instruction begins, executing. During the second cycle, x is still 1. During the third cycle, x is still 1. After the third cycle, the add x3 instruction finishes execution, setting x to 4. Yeah, would be the same. Maybe you can learn something by looking at the value of x, of the x register throughout the execution. For now, consider the signal strength, the cycle number multiplied by the value of the x register during the 20th cycle and every 40th cycle after that. That is during the 20th, 60th cycle. For example, consider this input, blah blah blah. The interesting signal strengths can be determined as follows. During the 20th cycle, register X has the value of 21. So the signal strength is 20 times 21. The 20th cycle occurs in the middle of the second add minus 1. So the value of register X is the starting value 1 plus all of the add X values up to that point. During the 60th cycle, register blah blah blah. The sum of these signal strengths is, okay, find the signal strength during the 20th, 60th, 100, 140, and what is the sum of these 6 signal strengths? Okay. So let's take our example here. Copy. Example input. The example check is this one here. And our puzzle goes here. So let's start parsing. For a line in lines, we'll take our line, just call this variable. This is our and then I want to have a we'll just make a map where we record if you just insert for every cycle. Yeah, I will just do it like that. I would just say current register X, and this is register X over time, and this will just be a list of long, and we'll also make this a long. So then we parse our lines. We say line dot if line is equal to no op. Then we say register X over time. And again, we forgot the mutable here. Dot add the current register X. Else we take line dot split and we split it by the space, and we take the second part and we take it to long, and this is added, and then this operation still takes some time. So we push, and we need 2 cycles. And after that, we set the current register X is equal to plus equal added. So let me just at the start of this first cycle, at the start of the second cycle, add X instruction. During the third cycle, X is still 1. At the start of the fourth cycle, this is only done. So, and then we would need to take add the register over time, the edit, and then we would collect all the so we have another loop. This is then for I in while it's 20, it's a var. Index smaller equal smaller register over time dot size, and then we say var sum is equal now we could do that with a nice windowed function, but I think we can just do it like this in index, and then we say index plus equal 40. And it wants to have it on the step. The only thing I'm a bit, when does it now say it's 20? But I think we can just figure that out with the example then. And we should just initialize them with null. And then here is the end of our method, so we return some, this needs to be multiplied, so we have this register over time is sum plus equal index. So the only thing I now want to check, if we have the example input, we say this is the 20th cycle occurs in the middle of the second add -1 instruction. So yeah, I will just find that out, some toString by debugging. So let's fire up our program. Now let's keep a log for what we're running. Yeah, I think we would actually need to check it that way. Did it already run again? Yeah. Mm-hmm. 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 But yeah, so maybe 20 for the index itself. But we would need to. We want a 20th value, right? Maybe we need to do 19 here. Yeah, it seems to be correct. So it seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. In this system, there is no such thing as a vertical position. If the sprite's horizontal position puts its pixels where the CRT is currently drawing, then those pixels will be drawn. You count the pixels of the CRT. 40 wide, 6 high. This CRT screen draws the top row of pixels left to right. Count the pixels. CRT 40. Okay. The CRT draws the top row of pixels left to right, then the row below that, and so on. The leftmost pixel in each row is position 0, and the rightmost pixel in each row is position 39. Yeah. Like the CPU, the CRT is tied closely to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as a hash. Here are the cycles during which the first and last pixel in each row are drawn. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel hash, otherwise the screen leaves a dark pixel dot. The first few examples of the larger example above are drawn as follows. Sprite position, start cycle, begin execution at x5. CRT draws pixel in position 0. Current CRT row. Okay, we need to read the ASCII art and afterwards type it here. That's pretty cool, actually. Yeah, the only issue I have, I've still not really understood how this works. So let's read it again. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. In this system, there is no such thing as a vertical position. Okay. Why is the sprite 3 pixels wide and we only draw 1 pixel? Begin CRT draws pixel in position 0. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel, otherwise the screen leaves the pixel dark. The first few pixels from the larger example above are drawn as follows. But we always start with the lowest of those three that's lit? Or we start with any of them? Well, we do. This Cartesian draws the top row of pixels left to right. Okay, so the only thing we do is we only draw each pixel once. Okay, we can actually see that here. And if the sprite is at that position, then we are fine. Okay, that's, I think, even easier than I expected it to be. So, we will have an example input, we will have my input. We will not have an example solution for that. So this is part 2. We can actually do the same here. We have a list of x positions at that time. And the only thing we summed it up here, and but what we now want to do is we now want to just iterate over our I in 0 until 2040. 240 pixels, right? Could we say something about that? And if register over time, this is our first cycle, is equal to this is this one, and if the register is equal to I minus 1, or the register is equal to I, or the register is equal to I plus 1. Because this is the value, it's 1. Then we can, I think we can make it a long loop as well. Never mind. Then we want to draw, and we'll have this is our output, var output is equal to, and we'll just concatenate that. Output plus equal the hash, and we'll use a dot for nothing. And afterwards, I would just say output dot Can this windowed thing actually do that? It's 40. And we would have this 40 and we would join those and would join those by \n. And this could be our matrix. And then we says matrix, and we also return the matrix. So yeah, the first line looks correct. After that, no. Allowing the program to run completely causes the CD to produce the following image. So it would start over again if I've understood that now correctly. So we would actually want to have a loop from 0 until register over time.size. We will just, well, screen position is I modulo to 240. And our screen position would then be this one here, be the I here. And output is a list. Let me array of chars and why it doesn't actually matter, right? Put in a char here. The only thing is we want to have 240 elements. And then for the output, we just say output at screen position is equal to this. But I've not, I think we will. I'm a bit unsure about if we would override one or if we wouldn't. So I'll leave that for now. Maybe it needs to be a toInt. And afterwards just output map it equal null. If it equal null, then we take the dot, else we take the hash itself. Then we and how does our matrix look? Our matrix doesn't really make sense by now, so at least let's check for that. Join to string without any separator, and I think we don't want it as a method, we want it like this. Yeah, this is still the same stuff. So we're actually getting our first line. But for some reason, which I have not really understood by now, we're not getting the second one. So we actually only have that many lines. So we can also have a look at our register. But our registers actually never exceed the first line. We have 240 instructions, but our value does not really get there. The first few pixels of the larger example above are drawn as follows. Yeah. Allowing the program to run completely. No. Or there is no horizontal. You count the pixel of each CRT. This CRT screen draws the top row of pixels left. So we also need to the screen position. Maybe that, but we'll also need to consider that the register will always be taking modulo 40. Maybe it's that is the clue, I think. But even no, not the register. We have the screen position, which is the actual position. But we also have a line position. And we will actually need to check against this line position. So the screen position will just continue. We'll be fine with that. We have the eye here. And we will check against this one. We'll check if our register is in this position. And this is our full output, I think. We have 5 dots at the end, and here our line has also 5 dots at the end. Happy with that. Then I want to check on the matrix. I think the matrix, this thing is just not working as I wanted to. So just that I want to find out how this window function works. Evaluate the expression line dot window, and we take a window of 40. And we want the step size to be 40 as well. And then we want to join those. Join to string with a \n. For printing then, okay. So I thought it will automatically take we'll put it like this for need that here, I think. And then we print it like a matrix. And then let's see what happens. Okay, I might need to join it. Stop and rerun. How? I really don't know why this lambda always tricks me. So. Yeah, it looks at least kind of the same. Copy this part. Yeah, we'll find it. Fine. And then I think we could have actually done that. New file example dot check, add, paste it here. And then let's run it. E, 8 capital letters, yeah. Okay. ERCREPCJ. These are 8 capital letters. So, yeah, thanks for joining in. We'll want to, we have the correct solution here. No, we have some solution here printed. This unfortunately doesn't match because we only read the first line here. So I might fix that so that our check file also does that. So then this is nicer as well. So thanks for joining in and see me struggle during understanding this CRT screen. Hope you join tomorrow again and have a nice day.